Hey, this is Bill Trombley from Trombley Tool in East Troy, Wisconsin. This is video number 3 in the video series that we're doing on building the gas tanks for the 1931 Curtiss Wright Travel Air 12W. We're making 2 tanks, so we got 2 customers lined up to build tanks. And what this video is about is just some of the basic stuff that we did for building the internal structure. This will be somewhat of a shorter video, then we're going to answer a couple of questions that people have had that have popped up. So as you can see here, we have the structure. This is for one of the tanks. And in airplane terms, we call this a spar that runs span-wise, and then a rib that runs fore and aft. On an airplane, any structure that runs fore and aft, like from the firewall to the tail, is a longeron, and then spars are span-wise. So of the 3 tanks that we had, one of them actually had a spar in it. The other 2 tanks that we could tell were built, we think just a little bit earlier, didn't even have a spar in it. And those were the ones that were broken up the most. All 3 of them had internal damage, but the ones with the spars had the least amount of damage. So we talked to both customers, and the guy whose tank didn't have the spars in it wanted the spars put into it. And I think it's a great idea. So it adds a lot of more strength, obviously. All of these parts are built out of 5052 aluminum, 5052 H32 by 50 thousandths thick. And you can see here, that's for tank 1. Tank number 2 is also built. The only thing we have to do is just rivet the sections together. We're going to do that in the morning. I don't mind shooting rivets by myself. I do it quite often, except for when I have to use the angle set on the rivet gun. So generally I hold the rivet set from turning while I'm shooting the rivets, so then I need somebody to buck the rivets. So we'll do that in the morning when it's really easy. It's only 5 rivets per rib. We changed the design slightly in that regard. We added some more rivets than what the factory had. The factory only had 1 rivet holding that together. We put in 5. And in a future video, I'll show you why. We'll pull out the original tanks and you can see inside the damage and then how they were constructed. There's a couple of little changes that we made. We made it much more of a design that you would see in World War II or more modern than that. So, but I thought one of the things, and this popped up a number of times, people ask me, how would you bend something like this, a channel piece, and have it so that when it was bent, you would be able to measure it and it was accurate to what you wanted. To give you an example here, I got 3 independent spars, and yet when these are all folded up and everything's riveted together, I need the overall length to be correct. Right, because the tank, when it's all finished, fits in an opening, but there's a finished tank size. We want that to be right, and how do you do it? It's interesting to see how some guys do it. There's 3 ways that I've seen it done. One of them is you could calculate it all, just do it all mathematically. If you look in document AC 4313, which I have showed this document in the past, acceptable methods, techniques, and practices for aircraft inspection and repair. There's a huge section in here on bending metal and bend allowances and minimum radiuses, setbacks, and then how to determine the K factor for the radius and everything for when you're doing the bend work. And here you can see an example like that right there on how you would calculate all of that. That's one way. Have I done it that way? I've never done it that way. It's not that I'm bad at math. I'm usually quite good at it. But it's a challenge. The bend radiuses, it matters then what kind of brake you have and what kind of shoe is on it. And you can chase your tail on it. If you picture it's a a straight section of material through a radius, well, that radius there, it's called arc length, would be where that starts and stops to go into the next section. There are modern day software now, machine software that will do that and put that calculations in. I know a guy that uses it. What's another way of doing it? I've also seen it done this way. It's just purely guess. And I've seen guys, and their parts look like it when they're done. Nothing straight, nothing lines up. They just stick a raw piece of material in there, set the back gauge, bend it and measure it and go, oh, that's off, and just recrank some more in and measure it, or bend another piece, measure it until they kind of get what they want. That might be great if you're not the one buying the material. It drives me crazy. So how do I do it? I take a scrap piece of material, and this rib here, we wanted a 3/4 inch flange. So I made this scrap piece 3 inches overall length. Then I took and I scribed a line that was exactly 3/4 of an inch in from both edges, and I bent it. And then I took my caliper, I can use my scale here, and I measured it, right? And then you go, oh, well, that wasn't exactly what I wanted. So I take another piece of scrap, readjust where the bend line is, and I bend up another scrap. So here, this 3 inch piece, my bend lines are 11/16 in from the edge, gives me exactly 1 3/4 across here. So then I can take now and use math to now go, well, this rib is 6 3/4 of an inch high. So I have to add this much extra material and set the bend line at this position, and everything works out. It might seem like a lot, but it's not. It's a simple actual bend it and actually measure it, and then go from there and adjust. It's a simple process. And by doing that, what it does is it takes out what is the bend radius on my brake. How far should I set back the offset on the back? Bend up a test piece, a coupon, it can be 1 inch wide, direct measure it, make your settings. I call it like a storyboard. I wrote it right on there. This one here was the first piece I did. It was 4 inches long. Made my adjustments, checked it, and went, now it's repeatable, went to town, built these pieces. And now when I take a tape measure on any of them, all the ribs are the same height, or all of the spar flanges are at the same height that match the rib, so that when this gets a straight edge going across, it spans it. I've had projects brought to me by guys and their ribs are off so high, they got these huge gaps. Well, how are you supposed to reconcile that? It's a pain in the neck. We had one project that was so bad, and yet the customer insisted on salvaging it, that the only way I could do it is I actually had to cut this flange off in the foot shear, build up a 90-degree angle. This flange was off so far on a project that was brought to me that I had to cut the flange off, build a 90-degree angle, set it in the right spot, and then rivet it on. What it was is it was a project that they invested a lot of money into, but it had a lot of issues with it. And it was brand new parts that we were building, and I had told the customer, the only way I can treat it is as if the airplane had crashed and slid down the runway, and fix the ribs, like repair them, to get us all the flanges lined up. Why is that important? We can't rivet over an air gap. It's as simple as that. I need it though that when the skin is touching this, that it's not shooting through a gap, right? I can't have the gap like this. It needs to be, everything is lined up and it's tight. So all of a sudden measuring stuff becomes more important. If you look at these tables here, I just got this steel table last weekend, and it's Blanchard ground flat, which is awesome, and I paid $125 for it. If you go on Facebook Marketplace. You can buy tables like this or just steel plates that are drops. You can buy steel surface plates that you would use in a machine shop. Welding tables. My welding bench is a fixture table. It has the 5/8 holes on 2-inch centers. It's a relative, it's expensive on one hand, but pretty damn awesome fixture table, and it was like $1,000, I think, ish. It's great. Lay out stuff that's actually flat and actually square and parallel lines and all that stuff. It makes a difference. Picture building a car frame that was crooked and now expect it to drive straight. It ain't gonna work very well. Same thing with this. You need to be able to build stuff so that all the flanges line up and everything is straight, square, stuff like that. It's worth the time to do it. So how to do it? Simple piece like this. There's a local laser shop that's been doing our laser cutting and big, huge press brake work. I mean, we've known those guys. Father runs the company, the family works there. We've known them for 30 years now. The company where my brother and I started working at used them. And then when we went out on our own, we used them. Just great group of people. And I was up there and I asked him, how do you calculate all this? And he goes, well, we just take a piece of scrap and we fold it up and we just direct measure it, program in the offsets, because they got computer controlled CNC press brakes, and do that before they take a big sheet of material and just, hope for the best. So it's just something to think about. It makes this stuff a lot easier. So we had 2 questions that came up, and one of them, I think I understand what the question was. And if not, just reshoot me the question and we'll keep doing it until we get the answer you're looking for. One of the questions is how did I determine how big to make this corner hole? So if you see here, this is bent 90 degrees this way, 90 degrees this way. So I cut out this corner and then I drilled that hole. How big do you make the hole? I don't have a good answer for that, but maybe this will help. I make the hole so it's bigger than what the bend radius would be, so that the hole is actually out into the field of it. And what does the hole do? It prevents a stress riser in the corner. If you don't have a hole there and you fold up any piece of material, maybe unless it's like 19 gauge AK steel or something like that, but you'll definitely see an aluminum. A crack will already form right there in the corner. So it's a stress relieving area that's put here in the corner. So generally a 3/16 hole is what I would use. And that gets it so that at least the hole is not in the bend radius. These are bigger. These are 3/8 holes. And how I came up with that is these here are baffles in a gas tank. And these here are fuel drain back holes to make sure that the fuel drains to the sump. Well, I didn't want that in any corner that you could get a possibility where fuel would pool in the corner. And I don't have a much more of a scientific process than this, other than I had the fuel lines. This is the fuel fitting that screws in the bottom of the tank. The hole in the fuel fitting is 5/16. I punched the corners at 3/8. I didn't want that in any way a restriction was greater than what the fuel flow would be out of the tank. There's so many other holes and places for fuel to bypass, I don't think it'd be a problem, but that was how I justified it. So that's why if you look at these and on the TV it might look like, well, geez, those are bigger. That was why. But I don't have any better answer than this. But I'm completely good with it. The other question we had, and this is from a friend of mine, Ryan, he said, how did you determine, what is an easy way of determining aluminum material grades? And I don't have a good answer for that that's simple. To me it's simple. And how do I do it? I do it by checking the material hardness. Here too in this 4313 document is a way of checking it. And what that would be is hardness testing the aluminum, and it's done, I believe it's Brunel hardness testing. And it would tell you, Vickers, oh, what am I getting at? No, Brunel hardness test. Brunel is the most common one that is used for aluminum. And what that will do is it'll tell you where the hardness comes in, and from there you would look at the chart and it would tell you if it comes in at this hardness, more than likely it's this kind of grade material. There's this device here. This is what I have in the shop. I have a Rockwell hardness tester, but that's for steel. You can't get the Rockwell scale down low enough because of the softness of the aluminum. So that's why they go to Brunel. And this here is a handheld device. It's made by a company called Barber Coleman, called the Impressor. Made here in Rockford, Illinois, which is not far from here. This was a used purchase that I paid $30 for. Checked the calibration, everything was in spec, and I use it. This company has a spec sheet that says if it tests here, it equals this material. If it tests there, it equals that material. Is there a chemical test you could do at home? There is, but it generally will tell you if it's 2024 or not. 2024 is high in copper. I just want to make sure I get that right, so the guys aren't looking at me and go, well, that ain't true. But none, yeah, it's an alloy that's high in copper. So there's a sodium hydroxide that they'll put on there, and it'll actually turn because there's a percentage of copper, it'll turn copper black, so you'll see that wicking through the edge. I don't use that. The hardness test is usually close enough for us. Another thing that I do, and I've had to do this with European materials, or a material that I know is not of the most common grades that we have here in the US, is I send it out. I send it to a metallurgical lab. We have one here in Milwaukee. It's a $175 test. Usually you get the results less than 24 hours. I mean, it's pretty darn quick. And that will give you the whole material breakup of exactly what that is. And when we need to know, that's what we use. A device like this, it's perfect for this kind of an application. It's close enough. But if it's European materials from the UK or Europe, they don't have the same material aluminum grades that we have here in the US. Now they have something that might be similar, but that doesn't mean that their 5000 series aluminum matches our 5000 series aluminum if you were to test it with this. So if I know it's a European material, I wouldn't rely on that test unless I had more data to be able to do it. And for me, it's easier to just send it to the lab. You know, some people look at it and go, you know, that's a lot of farting around. You send this coupon out and whatever. And I disagree. Aluminum is much more sensitive, especially like if you're in a welded, as an example, to having the correct kind of filler rod and the correct kind of procedures for the correct kind of grade. And you don't want to be doing like a fancy car and all of a sudden have cracking because you selected a wrong filler material because you didn't know the grade, what led you down to a bad path. So it's something then it's worth the test. Or research it as far as buying a device like this. Actually, these even on Facebook Marketplace. The most expensive one I've seen was $100. Not that big of a deal. I think if you're going to be doing a lot of aluminum work, consider it. And then one more item, and then we'll be finished up for tonight. It's scuffing of the aluminum on the surface. I'll give you an example. You might be able to see that. Yeah, you see these lines coming through here, like that. What is that? It's shelfware. The material slid across the workbench and it scuffed it. And guys will look at that and go, stress riser, it's junk, can't use it. I disagree. So how do you know? It has to be a deep enough scratch to where you can actually kind of hook your fingernail into it. You can actually see it. A scuff on the surface isn't enough to do it. And how do you accurately define it? I don't know how to accurately define it any more than that. Guys will look at it, and especially like in 2024 aluminum. 2024 is alclad material. What is alclad? It's cladded with a coating of pure aluminum. It's cladded, it's bonded to the surface with 1100 aluminum. And it's done for corrosion resistance. So guys will see that little scuff mark and they go, oh, it greased through the alclad and it's junk. And I've told guys, I said, well, here, to prove you wrong, take a piece of Scotch-Brite and Scotch-Brite the aluminum. Take a scrap piece and just sit there and Scotch-Brite it and Scotch-Brite it and Scotch-Brite it and Scotch-Brite it. Or sand it. And you'd be amazed at how long it takes for you to actually get through the alclad. Because you'll know it when you get through it. The base material is grayer in color. The reason why the alclad is super bright and shiny is it's a coating of pure aluminum. It doesn't have any alloys in it. It's the alloys that make that finish look darker. I'm an EAA Warbird judge up at Oshkosh. You'll see airplanes that show up at Oshkosh, beautiful airplanes that were restored, all polished aluminum P-51 Mustang. And you look at it and you can see this ghost imaging through the whole side of the airplane, where they wet sanded and polished the airplane and they greased through the alclad. And no matter how much they polish it, that ghost image of that darker, duller color exists through the surface. And why? Well, a lot of those airplanes were either had paint on them at one time, so a guy scuffed it up, some paint guy, or it sat outside. There was a time when a P-51 Mustang was kind of a worthless airplane. You hear the grand stories about those airplanes being bought for the weight of the fuel that was in the gas tanks. So because of that, the guys didn't want to pay for hangar rent, so they tied them down outside. So they corroded. So now they go through restoration, they don't get reskinned, they sand them, they grease through the alclad, and you'll see it. So be mindful of that. If it was a corrosion on the surface, we can grind away 10% of the base material. As the standard accepted material for way of dealing with corrosion, I should say, is up to 10% is a kind of a baseline thing. Well, if it's 40 thousandths thick, do you think that scratch is 4 thousandths deep? More times than not, it's not. So I say that because I think there's a lot of good aluminum that's getting scrapped because some guys are holding it way too high of a standard. Yet I've seen other aluminum that looks like it was dragged behind a truck, and guys go to that too. So I'm just trying to show you where I cut through in all of this. So scratch is bad, stress riser is bad, a little bit of shelf scuff, don't worry about it. So I hope it makes sense. We had the inner structure done. We had to catch up on the second tank a little bit because of the way it worked out with the customers, but it's all good. And next step from here is we'll be building the end caps for the gas tanks. And so I'll shoot a video on that later. So any questions, put it down below. Like, subscribe, tell all your friends, and thanks for watching.